Okay, I have promised you videos proving two things. The first is the work energy principle, which is that work is the change in kinetic energy, okay? And the second is that for a changing potential, that the work is negative times the change in potential for a conservative force, okay? So I'm going to go through and show you both of those things now and where they came from. So first, the work energy principle. Okay, so we know that the work done by some net force F is the integral F dot dl along some path from A to B, okay? And we also know that the net force is the mass times the acceleration, okay? And we said when we were first talking about circular motion that we could define our acceleration as having a centripetal and a tangential component, okay? And this is true for circular motion, but it's also true for any motion along any path. So if we imagine a path like this, okay, that goes from A to B, and we've got some force, for example, here at some position along that path, okay? That means that our acceleration at that point is in the same direction as our force. So our acceleration, we'll write like this. And it's got some component that's tangential to the force and some component that is tangential to the path and some component that is perpendicular to the path, okay? And we can consider that perpendicular to the path component of the acceleration to be the centripetal component of the acceleration because it's the part that makes it curve, right? The tangential component is the part that makes it change speed, and the centripetal part is the part that makes it curve, okay? So we're going to put these ideas together, right? And when we were talking about the idea of a tangential acceleration before, we said that the tangential acceleration was the change in the speed, right? And then if we have an object that's moving along this path, okay, at any time t, its velocity vector is given by the change in position vector over time, right? It's wherever it's moving on its path, the velocity is the change in that, okay? So we are going to put those things together, okay? So we've got that our work is integral of A from A to B of F dot dl, okay? We're now going to put in that F is ma, and we're going to put in that dl we can put in v dot dt for, okay? So now we've got that this integral is mass times a dot v dt, and now we're not integrating from a to b, but from time at which it's at point A to the time that's at point B, okay? All right, and then now the component of the acceleration that is parallel to the velocity is the one that will come into play in this dot product, right? And so this is equal to the integral ta to tb m at dot v dt. And remember, at is the change in speed over time, and so this at dot v is equal to dv dt V, because those are in the same direction, right? And so then the work now is equal to the integral TA to TB M dV dt is V dt. Okay, and now we can realize that this equation is also M integral VA to V dV, okay? And so now, let's do this integral of V. So that integral is just 1/2 M VB squared minus VA squared, okay? So now, if we define our kinetic energy as 1/2 mv squared, then this last equation is kb minus ka, or the change in kinetic energy. Okay, and this is getting kind of long, so I'm gonna make the potential energy one as a separate video.